Do I still have the pleasure of your company?
Yes.
Yep, I'm here.
Last week, we got used to rotations in 2 dimensions. We worked them out this way, that way, and everything was obvious and familiar. So let's do rotations in 3D, and we can cheat in the sense that we can compose them from 2-dimensional rotations. Here is how. Take a coordinate system zxy, then rotate it cyclically. So x goes to z and y goes to what used to be x. So this is the same coordinate system, but relabeled cyclically with 3 axes. And do it one more time. So the z ends up here, x ends up there, and y ends up here. So, this is the same coordinate system, but you call them zxy, Bar calls them xyz, and Sarah calls them yzx. It's okay. Now, put a vector in the xy plane. So this is the whiteboard, and this is the z-axis, and we have a vector in the whiteboard, and we rotate the whiteboard or your head a little bit. It's called active or passive transformations. And as a result, we see a new vector, which has a property that z component hasn't changed. And the xy rotation is just the usual one that we already know in 2 dimensions. So the new one, z component doesn't change, and we have rotation in 2 dimensions, which is in xy components. We call this phi 3, referring to the 3rd axis, and we call this rotation don't touch x, don't touch y, and just rotate around z-axis. And I'll do honest work. I'll do calculation for you, thing that I hate most. But I realize I have to deal with students, so that's my that's my
There are any engineers here today.
They're all voting, you think. Wash, rinse, and repeat. In this case, we don't touch x-axis. We rotate by angle phi 1, which is in a yz plane, and we describe it by the usual 2-dimensional rotation. And in the 3rd case, we don't touch anything that's pointing in the y direction. So that's just multiplied by 1. And now there is one thing that I want you, to comprehend. Think about it, because z has to be rotated in the x. It turns out that this minus sign that used to be here, lands in this corner by cyclic symmetry. And other than that, it's rotation by angle 2. And these are 3 rotations, and we're in business. We know that we can write rotations in 2-dimensional in exponential form. So the natural thing, there are infinitely many rotations in continuous group because every angle is a group element. But we can parameterize this by a real number in just a single generator in 2 dimensions, where these little eyes are stuck here to make this thing Hermitian and this thing a unitary transformation. So it's a subgroup of U group, if you wish. And let's redo this in 3 dimensions. So we just go for it. We say, look, I can put my 3 phases into a vector F1, F2, phi 3, not F phis. And this is now some kind of vector in some parameter space. This is not my original coordinates. This is something that will parameterize the transformations. And then I can construct this combination phi dot t, where there are 3 matrices, 1, 2, 3. And, we know from 2 dimensions what they look like. They should look like 0, 0, 1, minus 1, or I minus I in the particular rotation for each rotation. So the first one will be phi multiplying a matrix dot touch x. In exponent, that means there is a zero. E to the zero is 1, so that's how the group element becomes 1. And then you have minus 1, 1, and everybody else is 0, because this is just rotation around the x. Or rotate around y-axis, and you have 1 and minus 1 here, and zeros every place else. So, that was a matrix. We didn't touch anything to do with y, so there was all zeros and zeros in the corners here. Plus, rotate around z-axis, and that one says, don't touch here in z direction, but, skew the whole thing around in xy plane, minus here, minus 1. So these are very simple sparse matrices. And this product is a matrix. It's a Hermitian matrix because the three matrices are Hermitian. I should be putting I's here, but, let me just say that I times T, I times T is the real numbers. And that now describes a finite rotation by exponentiation. Rotation depends on a parameter arrayed in a vector. In exponential way, it's minus I, parameters times the generators. These are matrices, but there are three of them, and that's what dot means. So, done. Nothing could be simpler. But, wait a minute. We need closure. It's a group. So I should be able to say I first rotate by some bunch of angles. Let's call that angles labeled A. So 3 angles at the original time. And then I decide I'll do it again. So rotate by 3 angles. And that's supposed to be a group element. And it should be. Rotation followed by rotation is rotation, right? So it should be something like phi B, phi A. But that doesn't work if you try it. You can multiply this. These are, arrays of things. And what does this mean? And of course, we were being stupid because when we wrote this, we just bravely put all these generators into exponent. But we know that these things don't commute. So if I multiply dot BA, and I compare what happens if I do A first, B second, or B first, A second, and I compare them on the level of these generators, it turns out this is not 0, as I'll show now, although explicitly computed. So we have to go back and think, and that's what Sophus Lee did in middle of 19th century, a brave Norwegian. And here is how the first, not very intelligent, but totally explicit calculation works. So let's see what happens if I take 2 of these generators in 2 orders. How does that work? So, on infinitesimal level, I have 3 matrices parameterized by infinitesimal small angles. And if I fill them in, I'll get the usual thing of the sign, only the leading term survives. There is nothing happening around the axis of rotation, so there is 1 and 0, 0, 0. And, same thing happens here as I rotate around y-axis. Well, this is, remind you what am I looking at? I'm looking at these 3 rotations, this one, this one, this one, and I'm keeping the leading terms in sines and cosines. Right now, I'm just leading term in sine is just sine is proportional to its factor, the leading term. So that's what I'm writing here. And this is 3. From here, minus sign is this minus sign. This is this guy, 1, 1. And then there is this guy. And we just have to remember that the sign has migrated down there. And now, usually we stop at the linear term in this expansion, but cosine should contribute something, and that happens only in the second order when I expand this cosine. So if I keep the second order here, then I get cosine terms here. So that's what infinitesimal rotations looks like if you keep the first 2 orders in expansion. For the sine, next term is cubic, so that's what we get. And now I read off my usual generators. So here I get minus 1, 1 from these 2 guys. And everybody else is 0, so let me fill it out. From this guy, I get minus 1, 1, and everybody else is 0. And from this one, I get minus 1, 1, and everybody else is 0. And these are the generators. This one rotates around z-axis, so it's called 3. This one rotates around x-axis, it's called 1. This one rotates around y-axis, called 2. And I'm carrying this I in here, so when I multiply it, I just get numbers here rather than i's. But just to keep track of unitarity. So now that we have these generators explicitly, we can compute the commutators. And it suffices to do the calculation just by taking one small angle in x and y directions and no angle in third. So it's good enough to make it the same. I don't need to do it, but it's quicker this way and gives me the results. So what is commutator going to be? I'll first rotate around y-axis, then I'll rotate around x-axis, and I'll subtract from it. Even if you don't think you know, that rotations don't commute. Take this book and you can rotate it this way and that way, or that and this way, and you get different. It's easy for you to convince it don't commute, at least at 90-degree angles. So, you expect that this will give us something. It's a rotation that's a small angle around, but it's just one angle, little small angle. So I can drop this index around axis 1. And if I expand it to first few terms, the first term in Taylor series is always just identity. It's e to the 0. The second term is this guy. I mean, the first Taylor expansion term, and I'll keep also the second term. And I'll forget the rest. Now, the first term is just identity matrix. I don't feel like writing it. Now, the second term is, a pretty sparse matrix. It's linear in phi, and it only has 1 and minus 1 here because everybody else is just zeros. I can fill it out. But it only rotates it in YZ plane, which is this part. And then the next term inherits the property from two-dimensional rotations. This property here, that when I square the generator, I get minus 1, but ignore it for the moment. So squaring the generator of two-dimensional rotation, that'll be also true when I write it as 3 by 3 blocks with nothing happening in 3 directions. So I find out that this is 0, 1, 1, 0, 0, 0, 0, 0, 0. And notice, what's going on. This is not identity because we have 0 in the X place. So I can't stick it in here. So that's what one of these guys looks like. Now I have to multiply them and subtract from it the other order of doing it. So I need to also know what happens if I rotate by the same angle around the y-axis. And that's just the same story. If there is an identity, there is a plus. And now this guy is rotating around y-axis, so it has zeros every place except in these two places, delta phi. And then I have thing that's identity in the XZ plane because I'm rotating around X, it has zeros every place else. So now it's easy to evaluate this product. So I first rotate about y-axis, and then I rotate around x-axis. And I just multiply these matrices, so I always get identity. Then for the linear term, when I multiply these guys, I pick up linear term either from here, from this guy or from that guy. So I get T1 plus T2 here. Or to get to the second order term, I multiply this by the other one, so I get minus I d phi squared. That's one way to get second order term. Or I keep these guys, which are always second order, and they just add up from squaring one matrix or squaring the other matrix. If I do the same thing in the other order, I want to subtract, rotate around X, followed by rotate around the y, then what happens is nothing changes in this part of the expression because this is symmetric in 1 and 2. So this part is the same, but it has a minus sign in front because I'm subtracting. Well, this one is actually different because, I picked up rotation around 1 from here, followed by rotation by 2 from here. And this is of order I delta squared 2. So when I subtract them, all this stuff is 0. And the reason why I had to keep the second order is that that's the first non-vanishing term. It's minus I delta phi square. And it's a product in one order minus product in the other order. In other words, infinitesimally, the difference of these two operations is a commutator of the generators of these two rotations. And it's easy to compute, so I have to compute a product of T1 times T2. This guy has minus 1 and 1 here because I'm rotating around the x-axis. This guy has 1, minus 1, and zeros every place. I multiply this matrix, and the only thing that contributes is this column multiplying that row, which is here, and everybody else is 0. Super simple. Now, if I do it in the other order, then, this matrix is here, this matrix is there, everybody else is 0. The only thing that survives is this column multiplying this row that's here, and everybody else is 0. Now I subtract them. So I get minus I square, from these two things here. These are in two orders, so that has a notation that's a commutator. Multiply them one way, subtract them in the other order. And this thing, when I add it up, I pick up a minus term here. So I get 1 minus 1. Zeros every place, but I recognize that's rotation around, general rotation on z-axis. This is minus I e generation around z-axis. In other words, the commutator of doing first rotation around y followed by x is actually rotation in the third axis. Very simple calculation.
Where did we pick up the I?
The i's are always trailing with this. If I multiply this, we did in 2 dimensions, and it just trails us here. To make the exponent unitary, we need a Hermitian matrix. So this is a Hermitian matrix. And unitary means there is an I here. Now, if we multiply them out, so if I take I times the generator, I'll get a matrix just with real entries. And that's why this I, this combination is just as ones instead of I's in it. So you know that we have to keep track of that because every group is a subgroup of unitary group, and we want to keep this unitary definition of exponentiation. So now, this super simple calculation, we have found the following thing, that the closure on a level of group operation, but infinitesimally, do one group operation, other, that's also rotation. But that means that the generators, have to satisfy this condition. And this I came from hermiticity. Now, these are arbitrary labels. Remember, I could rotate around z-axis, x-axis, y-axis. So they're just cyclic permutations of each other. So immediately it follows that if T2 is followed by T3, which means I promote these guys in here, I'll get I T1. And if I, cyclically permute it, so T3 comes in here, T1 comes in here, I'll get I to the T squared. This just comes from cyclic symmetry of the coordinate system. I can write this in a way which is foreshadowing the whole theory. I can introduce a new symbol called Cvitanović symbol. Which has 3 indices. So that's called a tensor. It's bigger than a matrix. It has more indices than a matrix, which has only 2. And it's defined in the following way, that if I take them in order 1, 2, 3, 1, 2, 3, this thing has to be 1. But for example, if I interchange 1 and 2, they'll get a minus sign because commutator picks up a sign. So if I interchange first 2 indices, I get minus ji, okay, is a minus sign. And because of cyclic symmetry, I can also shift a little bit and interchange this last 2 indices, kji, get minus sign again. So it's a very simple tensor. It's a 3-dimensional array of objects, but it has value 1 when all the indices are different and they're correctly cyclically ordered 1, 2, 3. Every time I mess up the order, I'll get a minus sign, so it'll be minus 1. And if any index repeat, I get a 0 because antisymmetric object is 0 if you have the same index. So that was a totally explicit simple calculation. And this thing has a name. It's called a structure constant. And how do you think about this object? Remember when we had finite groups, we had a multiplication table. And main result of the abstract theory of groups that every set of object and operation that has the same multiplication table is isomorphic. So you have to just solve the diagonalization for this abstract set, the multiplication table, and then you have all irreducible representations for anything. But because the exponentiating stuff, let me remind you what generators of unitary groups were. And this is a subgroup of unitary group. Instead of studying group, we studied E to the matrix H, and that had natural decomposition in a basis in terms of generators, this thing here. You're now at a special case of that. Instead of multiplication table, because stuff is in exponent, you need something else, and it turns out to be these commutators. So for finite groups, you have multiplications, and the table is, you multiply 2 group elements, you get a third one. So it has this form. But for continuous groups, you get commutators, and, I derive them for them. You just get them. It's not surprising. And that's what plays the same role for continuous groups.